Hello and welcome to Toddcast number 5. So continuing on with early part of organic chemistry, I want to cover bonding and orbitals today. So we've, up to this point, the first 4 Toddcasts have covered just connectivity of atoms, Lewis dot structures, formal charges, and just how we represent it. But this is where we transition into representation into more visualization of what's going on. So we can look at the interaction between 2 atoms in a couple ways. There's mathematical perspective, looks at the energetics, the favorability of how they interact. And then there's the visual perspective of actually what's happening between the nuclei and the electrons that they share. And then there's just the organizational aspect to figure out what turns into what. And we're gonna look at all these things for the course of chemistry. But for today, or this podcast, I should say, we're going to cover the concept of bonding. And so the theory behind bonding is that electrons are shared between 2 neighboring atoms, but it's only the valence shell or outermost electrons that get shared. The ones closest to the nucleus are held more tightly and can't be given away as easily as the ones on the outside. So just as we gain and lose electrons from the valence shell when this occurs for a single atom, same thing when it shares. So rather than lose an electron to free space, it's called ionization energy, it's going to lose its electron to a neighbor. Rather than gaining an electron from free space, called electron affinity, it's going to gain an electron from a neighboring atom. And so the same rules that impact ionization energy and electron affinity will come into play, but instead of it being electrons from who knows where they come from, they're coming specifically from another atom. So a bond we are going to view as a scenario where one electron from one atom combines with another electron from another atom and exists in a predetermined space called the bonding region. That doesn't mean there aren't such things as a bond formed from 2 electrons from one atom and no electrons from the other. It can be shared that way, but to start out, we're going to assume 1 electron from each atom. So if we consider hydrogen, again, hydrogen is 1s1. They each have 1 electron. That's our Lewis dot representation. Okay. If you recall from general chemistry, the 1s orbital is spherical in nature and relatively close to the nucleus. So I'm going to represent this blue cloud as the orbital, the 1s orbital, where the electron exists 95% of the time. As the 2 elements get closer and closer to one another, so the H's draw nearer, this nucleus and this nucleus are going to get close and they run the risk of repelling. But before the repulsion gets too great, there's going to be an attractive interaction of this valence electron to not only its nucleus, but if it gets close enough, it can actually feel this other nucleus. And so let me draw the nucleus, the proton, the hydrogens, so they get closer and closer until they get what's going to refer to as a bonding distance. So if they're far away, this electron on this one and this electron on this one, they're not going to really feel the other nucleus too much, but they'll feel it a little bit. They're going to repel each other a little, so they're going to move away, but they're going to be attracted to the positive. So it's this balance. As you move closer to closer, though, you start getting to a point where this electron can be in the middle. And when it is, suddenly it's going to still feel attraction to its original nucleus, and now it can feel attraction to the other nucleus, meaning it's going to have a positive interaction and want to be there. And if this electron's over here on that side, then it's fine. It's the repulsion of the 2 electrons isn't going to be significant. Because they're always in motion, it could also be this scenario. It could be electron over here, electron in the middle. And so if I just do that based on probability, then there's going to be electrons somewhere in the middle a lot of the time, and electron on the edge some of the time. So if I draw a region of space where it exists, where the electron can exist, it's going to be mostly here, with sometimes here and sometimes here. So if electrons go here to here, then this one might go here to here. And they'll move around and be shared. So this becomes a new region of space. So instead of these 2 original circles that we had, and I'm going to draw my circles a little distorted because they start to attract, but if they get too close, now the nuclei are so close that they repel one another. So this interaction might get too close. And so it ends up being the so-called optimal bonding distance between the 2 nuclei that allow the electrons to be between the 2 nuclei and make a more favorable attraction without the 2 nuclei getting too close. So a bonding distance is defined as the optimal positioning of the 2 nuclei so that the electrons can be shared between them but repulsion to nuclei isn't so great that it pushes them apart. Okay, so that's our visual theory. No math involved, just purely visual. So these two will come together, they get close enough so that they form this. And so what we call it is a sigma bond. So a sigma bond is when the electrons are shared between the two nuclei. So again, the nuclei of hydrogen are right in the middle. So there's my nucleus of that hydrogen, there's my nucleus of that hydrogen. And electrons prefer to be in here and occasionally here and here. So I said 25, 50, 25 before, but reality, probably more like 10, 80, 10. Okay, so we have this. You're never going to be asked about density probabilities in this class. That's more for physical organic chemistry. So in the hierarchy of chemistry, there's organic, that's what we'll cover. There's physical, which is mathematical analysis of how things work, a little more in depth. And then the pinnacle of it all, where it all comes together, is physical organic, where we do PChem applied to organic molecules. And so we actually look at the wave function and the probability of electron density. For us, conceptually, you just need to know this visual perspective. Sigma bond, 1s to 1s means the two orbitals involved are 1s's. Okay, now that's going to be one type of bond, very limited, H and H, but carbon and H is going to be so common, you're going to see that repeatedly over and over and over in chemistry. But this time, it's a 1s from H because that's all it has, but carbon can form from a hybrid. I've chosen an sp3. It could be an sp2 or an sp, but for the sake of keeping this simple, I'm going to do this. And hybridization involves, rather than having symmetric distribution of electrons, having an asymmetric. So there's more on one side, which allows it to orient and bond. So hybridization is necessary to form a bond, and a bond generates or forces it to hybridize, if that makes sense. So the cause and effect, chicken and egg, don't know which comes first, but as it forms a bond, it'll reposition or redistribute electrons so that there'll be more on the side of the nucleus that it's interacting with. Okay, so when this combines with this, you get a picture that looks kind of like that. So it's similar to this, but the cloud is a little bit wider simply because it comes from a two instead of a one shell. So one shell makes it smaller, two shell makes it a little bit bigger. Okay, you will not have to, you won't be judged or evaluated based on the preciseness of what you draw, but the concept of what you draw. So now notice it's a sigma still, electron density between nuclei, but between an sp3 and a 1s. Okay, so that's our visual. It's known as covalent bond. So valent bond is a sharing of electrons in a fashion where they do not have full charges. Ionic bonds involve the actual transfer of an electron, a plus minus, but this is one where they're shared. So each atom, again, is going to be responsible for putting in one electron. So if you form the bond, one electron from one atom combines with one electron from another. If they break apart, they each get one electron back, and it's known as homolytic because they each are involving one breaking and then just equal balance of atoms interact. So let's consider a more complicated molecule. Central carbon has 4 electrons. I have an O that has 1, 2, 3, 4, 5, 6, so it needs 2. So it could take up these 2 of carbon. I have an H that has 1, so it can only form 1 bond, so that's there. And I have O, which I haven't drawn as a bond over here, and I probably should have, but I collectively put it as an OH. That's an O with a sigma bond to an H. And so O has 2 lone pairs and 2 electrons, but 1 is used up in the bond with H. There's only 1 remaining bond or electron to form a bond. So we're going to get 2 bonds, a double bond there, single bond and single bond. So they will come together. We've done this as Lewis dot structure. So again, that's bond, that's a bond, that's a bond. So this is our more common way of representing this molecule. Carbon with a double bond, and single bond. Okay, so we're going to press ourselves a little bit. We're going to expand the way we look at these. But between these 2 atoms, you have carbon-carbon. I have a slight typo here that I need to fix, and that is, this is actually now sp2, because this carbon right here is involved in a sigma bond, sigma bond, and a pi bond, as we're going to learn. So this is kind of a or like, I don't know, which do we discuss first? So it's we're I'm teaching bonding about these bonds, and I have to write the bonds to come up with hybridization to figure out what the bonds are. So I know it's that same thing. Bonding uh, induces hybridization, and hybridization has to occur to have bonding. So in order to figure out what the hybridization is, like we did before, the steric number, 1, 2, 3 atoms attached to carbon. So we call it sp2. And so it's an sp2, but sp2, you know, is trigonal planar, which this is, so that fits. But now the reason behind it, the cause and effect. sp2 means it can form a sigma bond with one sp2 orbital here, one sp2 orbital here, and one sp2 orbital here. So one of these electrons is sp2, one is sp2, one is sp2, but one is at a p orbital. I want to emphasize that in the beginning, that was an sp2. That's an sp2. And I'll just say that one's an sp2, but that one has to be a p orbital because pi bonds are formed from p orbitals. And so you've learned this, hopefully, but just to review it, sp2 can form in sigma, sp2, or sigma, sp2, sigma. So hybrid orbitals go on to form sigma bonds, but pi bonds can only form parallel p orbitals on adjacent atoms. Okay, so here's my sp2 to sp3. Here is again, same typo, so let me get rid of it. It is an sp2 bonding to sp3 oxygen. And then there's an sp2 of carbon connected to 1s of H. Okay, and then there's one more bond, and that's the OH bond. But then there's also, as far as this carbon goes, it has a sigma, 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 which you've done. Sigma here, to the H, check. Sigma here to the O, check. And sigma here to that O, check. But we are going to have to make room for a pi bond. So let me get my sigmas drawn. The pi bond, note that it says it's between a 2p and a 2p. So the 2p here and 2p here, 2p here and 2p here, which means I need to go back and redo my oxygen as well. So convoluted, but again, hybridization necessary to make bonds, bonds induce hybridization. So they're going to go hand in hand. So now I'm going to go back to my oxygen, which actually has a steric number as drawn here, 1, 2, 3, 4. So I'm going to call this sp3. This one has lone pair, and pi bond, or sigma bond, excuse me, for a steric number 3, and it's involved in a pi bond. So it actually has to use a 2p, which means this one also needs to be corrected to sp2. So interesting, I just discovered something. If I have a pi bond, I cannot have an sp3 orbital, hybrid orbital, on either of the two atoms involved. Important to know, so I want to make note of that. That according to our convention, you use a p orbital for the pi bond, then maybe I have a short way of doing it. So let me just inventory. I have an sp, a p. I know pi bonds apparently can only form from p orbitals. If I pi that out, I'm left with an sp2, which comes all the way back up to here. The steric number of 1, 2, 3, 1, 2, 3, that helps me to know what hybridization is. But I want to emphasize that I can also get it this other way by looking at what the bonds are. Every atom that we're dealing with, carbon, nitrogen, oxygen, will have sp-p-p, the two shell to mix together to make hybrids. For every pi bond, which uses a pure p orbital and doesn't hybridize, I pi it out, and I'm left with an sp2. So I'm feeling pretty good about this. So the reality, these typos actually were helpful. So this one right here, I'm going to leave as an sp3 for now. In a future Toddcast, we're going to cover something called resonance, which will show that these electrons can be shared. And if they are, they have to be shared in p orbital. So note that I'm teaching something that, as of our information base today, I'm going to say is okay, but it's going to be wrong in about 4 or 5 Toddcasts. So I know it's a weird thing to do, but in chemistry, as we learn, we build things, we change what we know as we learn more and more information. So right now, early on, I'm going to say the one in a pi bond, sp3, or sp2, excuse me, the one in no pi bond, sp3. So sp2, because you use one of the p orbitals for that. Okay, and then last but not least, I need to add the H in. And so again, I want you to recognize what error I made. And my goal here is, and this is going to be awkward if you haven't had me as a teacher before, learning from errors is absolutely the best way to learn. I mean, I know it sounds really weird, but when you sit there and you have to double check and correct, learning studies constantly say that if you quiz yourself, and whether you get it right or wrong, if you get it right, reaffirm the way you thought about it. If you get it wrong, correct it. You will learn it much better. So I want you to figure out what I've done here. So I'm still going to say it's sp3. That's fine for now. There's no resonance to consider. But is hydrogen forming a hybrid? Oh, hydrogen is forming from the 1s. So I need to correct this one. So instead of being sp3, it is a 1s. Okay, you are going to have to do this on quizzes and homework. So recognizing when I make mistakes is hopefully going to make you more attentive to double check everything I do, which will get in the habit of double checking what you do. So everything is finally correct now. I have pi bond between a 2p and a 2b of the O, so P and P, leaving an sp2 for oxygen and sp2 for carbon to make that bond, an sp2 of carbon with a 1s of hydrogen, an sp3 oxygen to an sp2 carbon. And I want to put a little underline there because that's correct for today. Again, it's going to become sp2 when we go over resonance. And then sp3, and again, that'll be sp2 when we go over resonance eventually, but a 1s to an sp3. Okay, this is our picture. This represents the bond coming out perpendicular to the plane of the screen or page you're looking at. This is going in perpendicular. This is in the plane, and bond angles are approximately 120, 120, and 120 because it's trigonal planar. And I'm actually going to redraw that, hopefully in a way that will make it more clear artistically. That has to go behind there, and that's a 120 degree angle. Okay, a lot going on. That's our first touch with it. This comes with practice. Okay, so molecular orbitals. Drawing these becomes key. So now I'm going to be a little more specific. I'm not going to make those same mistakes as before. I learned from my mistakes. Now I know it. So I note that for this one, everything is single bonds, no double bonds or triple bonds. So sigma, 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 4, character number 4, so sp3 to sp3. So that's going to form a bond like that. And again, sp3 to sp3. This bond has a double bond, or this double bond has a pi bond, I should say, which means if I consider what's going on here, SPPP, I pi that one out, left with sp2. And then finally, this triple bond, it's going to be an interesting one. That has one sigma bond in the middle one, and there's 2 pi bonds. So in this case, I again have 3 P's and S and 3 P's, SPPP. I have 2 pi bonds, meaning it's left with sp hybridization. Okay, so now for the pi bond. I'm not sure why I did red and blue, but it looks kind of festive. So this pi bond is going to have to slide over. So if I move it over, it's positioned there. So kind of like we drew with the last one, we had an O, a carbon, an OH, and an H, and then the pi bond perpendicular to the plane of those atoms. It is going to become really important that you recognize the orientation of atoms because it's going to influence the reactivity, which side it reacts on. If something is planar and symmetric, then it can react top or bottom if it reacts with the pi bond. Okay, and then for this one, again, last one I should say, want to emphasize this is sp and sp. You have a pi bond here, there's one p orbital, but the other p orbital, if this is, let's say, a py or px or pz, whatever letter we pick, let's arbitrarily call it pz. This one has to be a px or py. It has to be perpendicular. You cannot have electrons in the same space. Meaning this one's going to come over just like this one did. This one comes over and it's going to look like that. So that picture hopefully makes sense where you have one pi bond here, and then another pi bond here. So one is in a plane perpendicular, and one is in a plane parallel to the screen. Hopefully that picture makes sense. It starts to get convoluted, and I'm not even considering the other sigma bonds. Shoot, so that had to be SP. Okay, so it's getting really visually impaired, but that's the way we're working these things. So here, I have a unique situation. I have oxygen, which SPPP, there's one pi bond, so that's pied out. On the other end, I have SPPP and a pi bond, so that's pied out. So SP2 for that oxygen, SP2 for that oxygen. But where it gets weird is the carbon is involved in two pi bonds. So one is pied out, one is pied out. Central carbon is SP. If you recall, SP results in linear 180-degree bond angle. So this molecule must be completely linear. CO2 is a linear molecule. So you have carbon in the middle, oxygen on the ends, and the same thing we had here. This pi bond comes in this way. It ends up because this carbon is already using the so-called PZ that we just described up here, then its other orbital has to be the one perpendicular to that orbital. So perpendicular to the plane of the page or plane of the screen. So the exact same orbitals we just did, only now this carbon is SP, this oxygen is SP2, this oxygen is SP2, but the orbitals are in parallel planes. Okay, you have to be able to visualize this. This is one of those I would highly recommend you redraw everything here. Okay. So if I separate the two pictures, this is the sigma bond between the two carbons. I'm ignoring the H's completely in this case. And then here are my bonds to the H's, and I'm ignoring the sigma bond between the carbons because when you start drawing it all together, it gets really, really convoluted really fast. Note that I didn't put one S, I just put S, and that's what all these bonds are. For the alkene, the double bond, again, the pi and sigma between the carbon, the sigma bond has electron density between the two nuclei. The pi bond always has electron density outside of the internuclear region. So the sigma and the pi, sigma is between the nuclei, pi is above and below, but not between the two nuclei. Okay, and then your other orbitals are here, the S for hydrogen and sp2 for carbon. And then finally for the alkyne, again, it gets really confusing. You have your sigma bond between the two carbons, the density between. You have one pi bond here and one pi bond in that perpendicular plane. And then these are your CH bonds here, S to SP, so SP hybridization. And I made it PX and PY. I said Z and Y earlier, really doesn't matter that much, but this one did PX as well. The X should be a subscript. I apologize because it's coming out really weird and ugly looking. So it's P subscript X, meaning along the X orbital, and PX and PY along the X and Y orbitals. Okay, pictures matter, visualizing matters. Okay, so the concept of bonding then, we're going to go into terminology. The bond type, sigma bonds, electrons are between the two atoms, two nuclei, and pi bonds where they reside in overlapping side-by-side p orbitals, but not between the nuclei. So for OChem, we're only going to worry about sigma bonds and pi bonds. And collectively, a sigma by itself is single, a sigma with one pi bond is a double, a sigma with two pi bonds is a triple bond. So we will use the term single, double, and triple bond, but for now, we're going to talk about sigma and pi. Bond length, like I showed in that picture, those two nuclei get closer and closer together. If they get too close, they repel. But if they get too far away, the electrons don't have that benefit of feeling both nuclei. So it's the average distance between the two nuclei when they are at that optimal spot where the attraction of the electron to both nuclei is high enough to make it favorable without causing repulsion of the two nuclei to make it unfavorable. Again, the sigma bond is the electron density between the two nuclei, and the bond length is the distance between the two nuclei. So typically, if we're saying the length of a bond, we're talking about the length of the sigma bond. Bond strength. Bond dissociation energy or the homolytic bond cleavage energy. Homolytic, again, lytic lyse to break, and homo means equal. They each break one electron. The stronger the bond, the harder it is to break. So we in chemistry measure the strength of a bond by the energy required to break it, the energy of light or the energy of the heat needed to break that bond. Free radical is a term we are now going to introduce. So let's say I have two atoms A bonded in this fashion with their shared electron there. If this bond breaks and one electron goes there and one electron goes there, it's how we're going to represent it. Things called bond arrows. So a single-headed arrow represents one electron moving that way and one electron moving that way. I'm now going to get an A with a free radical. Plus an A with a free radical. The radical stands for a radical electron. It is highly reactive, it's out there and unstable, but a free radical atom is one that has an unpaired electron looking to do something. And so I alluded to it briefly in the previous Toddcast where we talked about O2 being what's known as a biradical, meaning it has two unpaired electrons. Unpaired electrons want to be paired, they become highly reactive molecules. That's why O2 is so highly reactive. It's one of the few things that can react with completely stable molecules like alkanes. Okay. And then bond polarity, not all electron density is shared equally. So it is shared, but the more electron atom is the one that will hold on electrons more tightly and it will end up with a partial negative charge, leaving the other atom in the bond to be short-changed electrons and have a partial positive. The bigger the difference in the plus and minus, the more ionic character in the bond. But for our purposes, we're going to just look at the relative polarity and not really worry about ionic nature of bonds in OChem. Okay, so we have terminology, absolutely important. And so I want to consider bond length and bring you back to GChem. So if you recall, if you move left, right periodic table, atoms actually get smaller. Notice I've omitted the noble gases because they don't make bonds. I don't care about them. Notice I've also omitted sodium, magnesium, lithium, beryllium. They go over here. I ignore these because they typically form cations, and cations are not involved in covalent bond length. So we're going to deal with mostly this part of the periodic table when we talk about covalent bonding in OChem. We have our big three, but every now and then a fluorine can get involved, chlorine, bromine, or iodine. That's going to be common. Every now and then sulfur and phosphorus play a role. Boron is known to get involved. Silicon can do certain things. And so all these technically can be involved in OChem, but these are three big ones. Okay, so as I move across, it goes from larger to smaller. So Z effective increases. So it causes the shell to get smaller. So the atom gets smaller as it goes. Okay, going up and down, it shells. As you go up, you have fewer shells, so it's smaller. As you go down, it gets more shells, so it gets bigger. Okay, as a consequence, a carbon-to-carbon bond is long. Carbon nitrogen a little bit shorter, carbon oxygen shorter still. Nitrogen oxygen is actually going to be shorter than that as well. So big and medium, big and small, big and big, medium and small. If you think about it that way, they go across. Okay, shells again are the key thing. So for this, carbon iodine bond is going to be longer than carbon bromine, which is longer than carbon to chlorine and carbon to fluorine. Okay, nothing terribly challenging there. It's remembering the periodic table. And then the other aspect. So there's the actual size of the elements, but in a lot of cases, we're going to be dealing with molecules that only have carbon and hydrogen. And that's when we have to get into some of the rules in terms of hybridization. So if you recall, if you have more S character, so 50% S, if you recall, was SP, 33% S was SP2, and 25% S was SP3. So the more S character, the more S things, more acidic, more S stronger, and more S shorter. So shorter, so sp, more s characters, so sp is the shortest, sp3 is the longest. So I'm going to erase my terrible writing. Just to remember that, though, that SP is going to be shorter, SP2 is middle, and SP3 is the longest. So if we consider this bond here between an SP3, has 4 things and no pi bond, and 3 H's in carbon, so 4 things, no pi bond. So SP3 to SP3, big orbital to big orbital. Then if we consider up here, we have SP3, 4 things, but this one has a pi bond. So 1 pi bond means it's SP2. So big to medium, it's going to be a little bit shorter. And then I can compare it to this one, which is SP2 to SP2. So 2 big orbitals can't get as close together. A big and medium can get a little closer together, and medium can get closer still. So this will be my longest bond between 2 SP3s. This will be my shortest bond between 2 SP2s. And the other one's going to be somewhere in the middle. So we'll call it the middleist. So hopefully this seems okay. This is just logic. Will you have to identify relative bond lengths in a compound? Absolutely. Will you have to decide what things are planar? Definitely. Will you have to decide what orbitals lone pairs are in and available from? Definitely, absolutely, for sure. All these things are going to be part of your experience. So, covalent bond strength. Again, more S character makes it shorter, but it also makes it stronger. So shorter goes with stronger, longer goes with weaker. So if we consider, go back to the periodic table rules, the carbon to chlorine, carbon to bromine, because bromine's a little bit bigger atom, it's a little bit longer bond. The angstrom is 10 to the minus 10th meters. It's the common unit we use in OChem and bio, so get used to it. But as we go down the periodic table, the bond gets longer. That means it also gets weaker. So larger atom forms a longer bond. Notice that the longer bond, the 2.136, has less energy, takes less energy to break it. So we have the small, the medium, and the large, and the corresponding energy. So longer bond is a weaker bond. So larger atom forms a longer bond, which in turn makes a weaker bond. So we'll go ahead and consider another factor, because that's just what we need, more stuff. So in this case, this is going to show us the fact that, yeah, the chlorine plays a role. These are all really close in length. 1.785 to 1.799 is hairline differences. But when you start stacking on more carbons onto this side, so just a C with 3 H's, not that big a deal. But when you start putting more and more carbons attached to it, it's going to be what's known as electron donating groups. You're going to hear me say this a lot. So if these, through electronegativity, so if you recall, Fonck, Bull-Brish, that's going to be the relative electronegativity from most to least in organic chemistry. So carbon is more electronegative than H, so ever so slightly, just a little bit, H is going to give electrons to carbon. That carbon gives its extra electron, share it with this carbon, and in turn, this carbon has a little more electrons. It can cause repulsion and push this Cl away just a little bit. So electron donating groups allow the chlorine to move away just a little. So no carbons, it's 1.785. By the time you go from 1 to 2 to 3, it's going to add a little bit more. So notice the increase. As a bond length goes up, the bond strength goes down. Not much, but it does go down. So just note again the trend: shorter bond, higher bond energy, longer bond, lower bond energy. And then these R groups, the so-called carbon groups, are going to donate in. And I called it an R group just because some chemists years ago said instead of drawing CH3s over and over, we're just going to call them R groups. So if you see it like this, that's the same thing. Okay, so let's go ahead and consider what happens. So electron donating groups to C make weaker bonds. They share electron density, which repels the other atom away a little bit and makes it longer and therefore weaker. Here we see the same trend. We see the bond getting longer as 1, 2, 3 different CH3s come in. And as the bond gets longer, the bond energy goes down, the bond gets weaker. And then finally, we see this same effect with iodine. So we see it with the chlorine, and from 0, 1, 2, and 3 extra methyls. We see it in the bromine, we see it in the iodine. And we still see that the iodine bonds are longer than bromines, bromines are longer than chlorines, and chlorine atoms make a stronger bond because they're shorter, bromines in the middle, iodine's large. This is information overload. We have given you so much stuff here, so much bond information in terms of strength and length that you probably feel overwhelmed. So stop, catch your breath, and see the trend. There are two trends here. From chlorine to bromine to iodine, bigger atom, longer bond, weaker bond. One trend. And then the second trend, the more carbon-based groups on the alkyl or carbon end, the more they donate in, they make bonds weaker and longer. So weaker and longer go together. Okay. So just a note of terminology. This is called a methyl group. When you have one carbon attached, they call it primary. When you have two attached, secondary. And when you have three attached, tertiary. So that's what this means. Electron sharing, tertiary shares the most. You have three R groups. Secondary, the second, you have two R groups or two alkyl or carbon-based groups. Then primary and methyl. So electron sharing, electron donating groups. The more you have, if you have three rather than two, or two rather than one, or one rather than just none in a methyl group, it'll donate more. So part of OChem's stress, part of the thing that makes it hard in the beginning, is notice that I'm teaching something and I'm throwing in words here and there that you've never learned before. You do a lot of vocab building on the fly. The early part of OChem gets really stressful because you're learning a foreign language. You have to know the terminology and simultaneously pick up the concepts. So if you can distinguish the two as you go, keep a running glossary. So from this page alone, you probably want to put what an angstrom is. You want to put what the correlation is between the bond length and bond strength and the atom size and the bond length. You want to mention what a donating group is. You want to mention what an R group is. You want to mention what tertiary, secondary, primary are. So you have just learned about 6, 7, 8 new phrases, words, concepts in a very small window of time. It is overwhelming. Your best bet is to do it slow, methodical, and write it down and say it yourself as you're writing it. It'll help it stick. Okay, polar covalent bonds. So last thing to add is the nature of the polarity of that bond. They're not shared equally. Falkenbrish, got to know this. Relative affinity from fluorine down to hydrogen. It tells you. So an FO bond, F is more electronegative, so F will get a slight delta minus, O will get a delta plus. So as I put this up, if you pause it, guess which way you should go, and hopefully you see here that O is higher than N. So O should be your delta minus and your delta plus. So for CH, okay, some of you guessed, C is higher than H, so delta minus, delta plus. C and BR is bigger than C, so delta minus on BR, delta plus on C. So it's just a matter of seeing where things fit. S more than H, minus plus. Next one up, OH. O much more than H, so that becomes a lot more polar. Delta minus, delta plus. Ni, N is more than I, so N minus, I plus. CF, F is way up here, Cl is way down here, so this is a very polar bond, plus and minus. C and Cl again is higher, so plus and minus, and then finally O and S. O is up here, S is here, so O will be minus, S will be plus. OChem comes down to seeing where the plus and minus is, because a plus will always accept electrons from a minus. An O minus will attack a carbon plus, for instance. You're going to see that reaction over and over and over. Minus will attack a plus. Okay, so for this molecule, carbon and carbon are the same, carbon and carbon the same. H's are about the same as carbon, but O is notably different than carbon. So this is going to be my delta minus and delta plus. And this dipole moment, we typically draw an arrow pointing to the dipole moment. I like to add a little slash over here to represent plus on the plus side. It is not mandatory. You won't see this drawn in books necessarily, but I like to add it in because it helps me to know what it is. The unit of Debye means absolutely nothing to any of us. We don't really measure in relative, but at least you should know, typically speaking, non-polar 0 Debye, that hopefully makes sense. And if it starts getting up into the 4, 5, 6 range, it is highly polar. So just something to hang on to thought-wise. This is still considered pretty polar. So, I mean, when I mentioned the other number, probably more along the ionic in nature. So these for covalent compounds, that's still relatively polar and still relatively polar. Okay. We're going to get into the impact of polarity towards the end of this block of information. So the Toddcast, probably around 8 or so. And then this one, everything's carbon and hydrogen. So the reality is they're almost the same. So very little dipole, and everything is going to pull equally. So that you're just pushing in the same amount this one over here pushes in. So you end up with a nonpolar species, or 0 debye. So with that in mind, it's time to say goodbye to debye. So thanks for tuning in, and I will see you at the next Toddcast. So have a great study time. This is one, definitely go back and review what you can. Thanks. Bye.